Let's try this problem. I'm going to go a completely crazy direction with it, which is related to one of the optional questions in the homework, but it's good to see new math ideas, right? So what if we just wanted to guess the answer to this? Well, based on what we've been doing with integration by parts, we might say it's the e to the at will probably still be there. The sine of bt will probably still be there. We know when we take integration by parts, we usually get cosines when we start with sines and vice versa. And we'll have probably e to the at times cosine bt. That seems like a reasonable guess, but you'd think that when we're taking integrals of sine bt, we're going to get a 1 over b, or a sine of integral of e to the at, we're going to get a 1 over a. So we're going to get some coefficients out front here. And there are going to be probably some big mix of b's and a's and stuff. So let me give us a new idea. Let's just call something out here q. We could call it smiley face or frowny face, just some letter completely unrelated to a's and b's. And over here, let's call it z. So if I do a good job guessing with my q and z formulas in terms of a and b, then this would be right. So how could I check that that was right? So I would take the derivative of that whole thing and hope to get the original integrand, right? So what would I get if I did take the derivative of all that? Well, I'm going to need the product rule here and the product rule here. Let's actually write that out. I know it's crazy. We're going to get q a e to the at sine bt. That's the first part of the product rule, plus q e to the at times b times cosine bt. And then from this plus, we're going to get z times a e to the at cosine bt plus z times e to the at times b times negative sine bt. Gotta zoom out to see all that, right? So is my guess right? Well, it depends on what the q and the z are. Let's think about that some more. What do I need it to be? I need it to be 1 times e to the at times sine bt, right? Because that's my original integrand right there. What about the cosine stuff? Can I kind of allow that to be there, but not really? Well, I could say plus e to the at cosine bt. How much of those are in my original integrand? 0 of them. So I need this expression to simplify to this for my guess to be correct. So let's think about what's going to go into this. This sine bt is occurring there and there. So I need this q times e, q times a, and this z times b with the negative. All those should get together and add up and simplify to 1. And then let's take some other color. How about green? And I need all the coefficients on the cosine terms. They already have the e to the at. I don't need to worry about that. But I need this q and this b together with this, the stuff from this cosine term, this z and this a. I need all those to gather and cancel and give me a 0. So let's write what we need there. So we have q times a plus z times negative b to equal 1, that 1 right there. And I need q times b plus z times a to equal 0. And is that something you can do? Maybe you've seen systems of this is a linear system with two variables and two equations, so that's good. So I need to find q and z to make this true. So I need to solve the matrix problem. So you can think of it as a matrix. If you've taken linear algebra, you could write it this way. My main variables are q and z, and I've got coefficients of a, negative b, b, and a times the vector q and z, and that has to be equal to the vector 1 and 0. So isn't that neat? We reduced a calculus problem to a linear algebra problem that you might have been able to solve in high school. The overall idea here is called undetermined coefficients. And that's something you might do in a differential equations class for solving one particular kind of differential equation. Did we actually solve a differential equation here? Well, a differential equation is where you're given the derivative and you're asked to find the original formula, which is basically what we're doing here, right? We're finding the antiderivative. So that's a fun sort of look at an alternate way to solve problems like this, a really complicated guessing check.